Now, Cluosh will talk about emulating AVR from scratch. Thank you.
So, hi, I'm Cluosh, and today I'm going to talk a bit about emulating AVR and the AVR architecture in general. After some technical issues, the presentation looks like this, but I think this will work out. I'm a student at Vienna University of Technology, currently studying software engineering. You can find me on Twitter and Mastodon, and I'm a member of the We Own You CTF team, which is probably the reason this presentation is happening at all. What are we going to talk about? We're going to talk about AVR. AVR is a microcontroller architecture, probably most known for the Arduino. And it's a popular 8-bit microcontroller architecture in general. You can find it in cars, in keys, everywhere. It's cheap and it's efficient, and it's easy to learn. So how did I come up with the idea of writing an AVR emulator anyways? It started with participating in the RHME CTF, which is an embedded CTF designed to simulate the embedded system in a car. And after the qualification period, they would send you an AVR board, customly designed, with a CAN bus module. And this was the main CTF challenge. So there were quite a few reversing challenges. Other than the reversing challenges, you could not read the firmware because the firmware was encrypted. And I just started statically analyzing the firmware, just looking at the disassembly. And I thought, okay, maybe it would be nice if I could execute this and see what it does. So I was looking for existing emulators that would help me find out what I wanted to find out, namely, what is the software doing, what is it sending on the UART port. And I was looking at mainly 3 emulators before that. I saw SimulAVR, I saw SimAVR, and I saw Atmel Studio Emulator. The Atmel Studio Emulator did not do what I wanted it to do, because I could not load a firmware image without any symbols into it and just run it. I just couldn't get it to run. It should be theoretically possible to give it an ELF binary with symbols, but it didn't work out. So there were SimulAVR and SimAVR, and SimAVR had more AVR cores implemented, so I chose to go with SimAVR. And I looked at the SimAVR repository and figured out I had no idea what I was doing, because unlike usual emulators or debuggers, SimAVR is somewhat hackable. This means you'll have to actually write code to get it running. But I didn't understand what I needed to do because I didn't understand the underlying architecture. So to get around that, I just decided to write my own emulator, mainly to understand what is happening in SimAVR and what is happening in the underlying AVR architecture. I also wanted to make it somewhat simple to use with a graphical interface, because I'm more the visual type. I like working with visual tools. And I just wanted to run a binary, firmware binary, and see what it does. And that was the birth hour of AVRS, which is my bird feeder. So I'm roughly going to talk about 4 points. I'm going to talk about the general architecture, or architecture which stays the same across AVR cores. I'm going to talk about how to emulate the basic stuff, and I'm going to talk about how to emulate peripherals. And then I'm going to show off the emulator as it exists now. So let's talk about the architecture. When we say AVR architecture, we mean something vague, because there are a lot of device-specific differences across all the existing AVR cores. If you write software for one AVR core, you can't just run it on any other AVR core. But there are things that stay the same across the architecture, which is that we have a Harvard architecture. So the program memory and the actual RAM or working memory is completely separate. This means you can't just write code into the RAM and execute it from there. You'll have to flash your code into the flash memory, and it will be executed from there. The flash memory is usually bigger than the SRAM because it's cheaper, and it has limited write cycles. So you can't just go ahead and modify the firmware while it's running as much as you want, because sometimes you won't have the ability to write there anymore. Yeah, you usually have some kind of EEPROM on the AVR board because you want to persist some data across reboots or resets. For example, if you have a car key, you might want to store the nonce of the key in the EEPROM. You also have different memory layouts per device, which is mainly on the SRAM side. The program memory layout stays usually the same with a few differences. So the program memory consists of the application section, and if your AVR CPU supports it, you'll also have a boot flash section. Where this boot flash section ends and starts can be defined with fuses. Also, if it can write and which section can write to the flash memory. Because you have a specific instruction which can write to the flash memory, but if you have permission settings, protective bits for the sections, you'll have to enable them in order to be able to write there. Because you might not want to have a firmware writing to the program memory all the time and waste your write cycles, but rather have it do it by the bootloader. And you can do the stuff like encrypting or decrypting parts of the firmware with the bootloader before you actually run it. The data memory is more interesting because it doesn't only consist of the SRAM, but it maps a lot of stuff in there. Things that are in the data memory on almost all devices or on all devices are I/O registers, which enables communication with peripherals, and some kind of SRAM. Everything else is usually not fixed, so you might have the first 32 registers in there, you might not have them in there. On AVR X-Mega, you have EEPROM mapped into the data memory. And the different sections of memory behave differently, because if you want to access registers, accessing registers is cheap. Accessing I/O register comes with side effects, meaning if you write to an I/O register, you'll trigger some side effects, and if you read from an I/O register, you're not going to get the same result, or not always going to get the same result back. And then you'll have the SRAM, which behaves as we would expect memory to behave. What else is there? You'll have interrupts. Interrupts are used for communication with devices, mainly in situations when you don't want to waste processor cycles waiting on some event to happen. This way you can, for example, put your AVR CPU into sleep mode and just wait for an UART interrupt to happen, signaling, okay, you got some data there, you can now read it. You can also do timing stuff. For example, trigger a timing interrupt every other second and perform some actions there. Then there's the instruction set, which stays mostly the same across cores. For the instruction set, you have to think of the program memory. An instruction is 2 byte long, and this is the word size for instructions. Then you have registers, which store bytes. Each register can store 1 byte, and you have 32 of them. And you have pointer registers, which can access memory with 2 bytes again. And the way those pointer registers work is they're just aliases for 2 other registers. In this case, the registers from 27 to 31, which will be addressed as X, Y, or Z in disassembly. This is a piece from a firmware binary. And here we can see a few things about the instruction set. On the left side, you can see the actual bytes in the instruction from the instruction stream. And you might note I said instructions are 2 bytes, but it's actually a variable length instruction set. You can have 1-word instructions or 2-word instructions. The 2-word instructions are rare. You have four of them. You have a long jump, you have a long call, and you have store to data memory and load from data memory. Because of the 2-word instruction size and the addressing working with word size in program memory, you can't jump into the middle of an instruction like you can do on x86 and just obfuscate it, but you can jump into the middle of a long instruction. So you could potentially hide data in a call or in a jump, which you might want to disassemble the second part of the instruction additionally, so you can maybe see if there's some data hidden. What else can we see here? We see that we have to load memory into the registers first. So we have a load store instruction. We can't just address memory with every instruction we have, like on x86. We'll have to actually load it into the registers, work with it, and then store it back to the registers, which makes it relatively simple to emulate later on. Since we have those pointer registers, which work with words instead of bytes, we also have some instructions working on words, working on pairs of registers in general. This allows us to efficiently work with the pointer registers. And additional to the long call and the long jump, we have relative jumps and relative calls, which, if you have a device with program memory less than 8 kilobytes, you can use to access all the locations in the program memory without using long calls. And those devices usually won't have the long call instruction anyway. So how would we go about emulating this now? First, we'll have to look at the instruction stream and decode the actual instruction to find out what it's doing. The easiest way for this to work is to have a table or more tables where you can just look up the high byte and look up the low byte. So you'll use the first table to look up the general area of what kind of type the instruction is. And then you'll use a second table to actually decode the instruction. This is a pretty neat way, because if you just decode it in table format, you'll easily find out if you missed an instruction or if you have an error somewhere in your instruction decoder. What does the table actually do for us? Now if we look at this, for example, if we look up an instruction in the instruction manual, we'll get this bit set, and we can apply this to the instruction stream. So we have 2 bytes here from the instruction stream. The instructions are read as words, and the words are read as interpreted as little endian. So even though these are the high 4 bits, those aren't the first 4 bits in the instruction stream. So we can see on the high 4 bits that this is a load immediate instruction, and then we know the instruction has to look like the table here. So we'll have some kind of register. a lot of instructions use 4 bits for registers, which means we can only access 16 registers, and we'll be accessing the high 16 registers. So in this case, there's a 1 in the instruction stream, which means we'll decode it to register 17, because we only have 4 bits for decoding, and we'll have to use the high registers. And then the rest of the instruction bytes is just the value we want to load into the register. Now, SimAVR, for example, now has the decoded instruction and just emulates it. I wanted to store the instruction in some kind of format I could work with, some kind of immediate format. This is just a Rust enumeration, which would be equivalent to a C union with a type tag. Now, when we emulate it, there's really not much more to do than doing what's in the instruction manual. In this case, we'll load the value into the register memory. Of course, there are instructions that are a lot more complicated, like this, to implement. You'll have to handle a lot of bit twiddling, because most arithmetic instructions use a half carry bit and a carry bit, and on most computers you can't directly access this information, so you'll have to perform the bit combinations yourself to get the flags and set it in the status register. Another important thing is, depending on how much program memory you have available, the size of the program counter changes. This means you'll have different behavior for stack instructions like call and return. So if it's enough, you can use 2 bytes for the program counter, but if you have a lot of program memory, you'll have to use 3 bytes. And you have to think of that when you use a call or a return instruction. Also, we have different instruction sets for different devices, which isn't that much of a problem, because usually if you have another device, it's just missing a few instructions from the instruction set, and those simply won't be executed. But in the case of an AVR Tiny, in the AVR Tiny 10, a few instructions have been removed, and at the place where those instructions were in the opcode space, there have been added a few other instructions. So you'll have to make some kind of exceptions for this. And yeah, the memory map, since you'll have to access the status register for storing some data during emulation, and the status register is in I/O space, you'll have to make sure to know if the registers are memory mapped or not, because the registers would be the first 32 addresses in the memory space if they are mapped, and then is the I/O space. But if the registers are missing, the I/O addresses shift by 32. So you'll have to take care of that too. Interrupt emulation isn't too bad either. Since most of the stuff is handled by the interrupt handler itself, you'll just have to set the program counter to the address of the interrupt vector, only if the global interrupt flag is set and if the interrupt is enabled in the corresponding bit for the interrupt. What's important to note here is that you clear the interrupt flag when entering the interrupt handler, because if you leave it on, you'll get pretty much a stack overflow, because the interrupt will trigger again immediately, most probably. You'll also need some kind of logical clock, at least. So most firmware will have some kind of timer functionality, for example, triggering an interrupt every millisecond or so. So the processor needs a concept of time. The easiest way to do this is just to assign 1 cycle to every instruction, and just use the count as a clock. This isn't accurate because different instructions take different cycles to execute, but it will do to just introduce some concept of time. And accuracy usually isn't that important for the use case, at least not for mine. Where can you find all this information? Usually you'll just have to look it up in a data sheet. If you now want to go ahead and implement all the AVR cores, reading the data sheets is a bit bothersome, and you can pull most of the information that's on the data sheet and that's important for you out of so-called PEC files from Atmel, which are just XML descriptions of what would otherwise be listed in the data sheet. Now you can't do much with the instruction set alone. If you implemented all instructions, as in the instruction manual, you'll still need some way to communicate with the outside world, or to perform some operation that is too complex to be included in the instruction set. For example, setting some processor settings or the watchdog timer. And for the sake of simplicity, I'll just treat all those devices the same regarding whether it's a device that actually communicates with the outside world or whether it's actually some processor setting that never leaves the processor itself. The peripheral communication happens mainly with I/O registers. This means you control the peripherals by writing to it or reading from it. As an example, I'll give a quick overview what you would need to emulate basic UART on the AVR side. We only care about the UART on the AVR side because on my case, which is reverse engineering AVR firmware, I just want to see what is being sent, and I won't actually send it to a terminal emulator. So I won't have to implement the actual UART protocol, but just how it behaves on the AVR side. And for the proof of concept, we'll use the registers as specified for the ATmega 328, because those change if you use another core. So we have a few registers specific to UART. We have 3 control registers, 2 registers to set the baud rate, and 1 data register where we store the data we want to send, and the data we want to receive is being written there. We don't need 2 out of 3 control registers for a basic UART implementation, and we won't need the baud rate setting because we won't send it anywhere. We're just going to dump the values. We might need the second control register, which enables or disables the interrupts, but for the sake of simplicity, we're just going to do it without the interrupts. Now, how would you go about implementing a peripheral? My usual process is I monitor what is the firmware actually doing, how it is communicating with the I/O ports, dump the trace of the communication, and look up in the data sheet what the communication means. Usually, it would be enough if you just go ahead and read the data sheet, but I personally think the process of tracing it and then looking it up in the data sheet is a bit faster and makes it a bit clearer to understand how it works. So the UART control register A is composed of a few bits, where we only need 3 for now. The rest is parity our parity errors we won't need to check because we won't actually send anything. And we can concentrate on the receive complete flag, the transmit complete flag, and the data register empty flag. Receive complete and transmit complete is pretty straightforward. If we're done sending something, the transmit complete flag is set, and if we have received something, the receive complete flag is set. The data register empty flag is relevant for sending data, transmitting, because we're only able to push data into the data register if the data register is actually empty. So if the data register empty flag is not set, meaning there is some data in the data register, we can write there, but it will just be ignored. And the emulator has to deal with this and think about this. So you can't just replace the value every time you write to it. So how would we go about sending? We wait till the data register is empty. We write to the data register, and then our emulator goes ahead and takes the value from the data register and does something with it. In my case, I'm just dumping it to standard out. You could essentially implement the whole emulator terminal on top of it and use the actual UART protocol to send the values. And once we've dealt with the data in the data register, we'll have to set the data register empty flag and the transmission complete flag. Of course, this isn't equivalent if you would actually implement the actual UART protocol. But since we're just dumping the values, we can treat the data register empty and the transmission complete as somewhat equivalent. So what about reading? Reading is basically the other way around, except we won't have the data register empty flag, because now the data register has to have some value, and we can just read from the data register. Now, how does that work when combined with transmitting? If you read from the data register, you'll get different behavior than when you write to it. Meaning, if you read from the data register, it will trigger an internal read queue, give you the top of the read queue, and move the read queue one along. And if you write to it, a whole other code will be executed. So you can use it both ways. You'll just have to remember how, and you'll have to emulate it. Just busy waiting for the receive complete flag to be set would not be very smart. So you can put the UART controller to sleep and then wait for the interrupt to be triggered. So yeah, what would you need to implement peripherals in general? As I said, you would need to monitor how the communication is occurring. You will have to look it up in a data sheet. But on the emulator side, it's important to track the memory access. Because if you don't track the memory access, you won't have any way to know if an I/O register has been accessed or not. You'll have to supply some kind of mechanism to allow handler routines, which you can just use as callbacks for read and write on I/O registers. And you'll have some kind of main handler where you handle the peripheral logic, for example, copying values around or dumping it to the command line or whatever you want to do with the peripheral. How does SimAVR go about this? This was one point I wasn't able to understand in the beginning. SimAVR has a pretty modular system for adding new components. And the main three interface points for those components are the interrupt definitions, handlers for I/O read and write, and internal interrupt requests. Internal interrupt requests in SimAVR don't have to do with actual interrupts on the AVR device and are used as some kind of signal slot mechanism for communicating between SimAVR modules. Defining the interrupts of the module is pretty straightforward with the SimAVR macros. And once you're done with defining your your interrupt, you'll just register it. As I said, you can put handlers on I/O read and write. You'll just write your callback function to handle the logic, what happens on a read or a write, and then you'll register it on a specific I/O register, and it will be executed once you write or read from it. And you have the internal interrupt requests, which mainly consist of three functions. You can register a callback, which will be called once the interrupt request is raised. You can raise an interrupt request, and you can connect to interrupt requests. Now, what you can do with this is, for example, do what I have done with the UART example, where I can just dump the values to standard out. In this case, you could do the same in SimAVR and have another module where you, instead of just dump the UART values to standard out, could collect data from all peripherals in one module and have this one module log all the interactions with the other modules. Yeah, and here are some SimAVR resources if you want to have a look at it. I recommend SimAVR. SimAVR is pretty mature, and if you know how the underlying architecture works, it isn't that hard to actually get into it. So if you want to use it for production reverse engineering, this is probably the best bet. How did I go about implementing my emulator? I used Rust as backend and C++ for the Qt GUI. The project is still pretty much ongoing. For now, only the ATmega 328, which is the Arduino core, and the ATxMega 128 is supported. I will release the code as soon as I hand it in my bachelor thesis, because the project is bound to my bachelor thesis, and I don't know if it's a good idea to release the code beforehand. Before we go to questions, let's do a live demo. So we have some firmware, which is actually a small reverse engineering crack a friend of mine wrote. And we load it into the emulator. And what we see is, we see the disassembly, which we get for free once we do the instruction decoding. And once we actually start the emulator, we'll get a trace of the instructions being executed. While the execution is happening, the functions will be recorded. Every time a function call is being taken, the function will be listed in the function overview. So we get function detection for free in dynamic analysis. And on the right-hand side, we can see a memory heap map, which is the I/O memory and the SRAM. So let's just start it up. And in the beginning, the program just copies data into SRAM or clears the SRAM, as we can see in the heat map. In the heat maps, the write axes are marked with red color and the read axis with blue color. And depending on how recent the axis is, it is either brighter or darker. So we might see something. Yeah. Since I don't output the UART in the GUI yet, I output it to standard out, and it just says enter your PIN. Now we can enter something. Yeah, but it won't give you any feedback right now. But we can see once we enter the PIN, a lot of other functions are being triggered, and then we could go and reverse engineer what the actual PIN is. And we can also stop and single step if we want to look something in detail. And that's as much functionality as the graphical user interface has right now. The backend is mostly complete. Now I just need to implement most of the GUI features. There are already some other features like memory view, but I have disabled them because I don't want it to crash in a live demo.